Okay, here I'm showing you the steps for sketching the graph of any real function. The first step is find the domain and range. The second step is find the x and y intercepts. The third is find the vertical and horizontal asymptotes, if you find them. The fourth step is find the critical points. I mean, when the first derivative equal to 0, or when the first derivative doesn't exist. The fifth step is finding the local maximum or minimum, or absolute maximum minimum, depending on the domain. Number 6 is find the monotony. 7 is find the inflection points. The 8 is find the concavity, and the last step is sketching the graph. Now I'm going to illustrate you how to do it using an example. And I'm going to sketch the graph of the function y equals 1 over 1 plus x. I'm going to rewrite the function in 1 plus x to the negative 1. That's to facilitate the calculation of the first and second derivative. The first step, I told you, find domain. This function is a fraction. There's no square root, there's no log, there's no even root. And the only problem you see in the function is the denominator, with the denominator, which is x plus 1, has to be different from 0. I mean, x has to be different from negative 1. Now, because the denominator is 0 and negative 1, you know, as the x's get closer to negative 1, the function is going to go to infinity. Now, I'm going to test it. Probably this is a vertical asymptote. I'm going to test the limits on the left side and the right side of the function when x approaches negative 1. And the limit is going to be limit when x approaches negative 1 from the left side of negative 1 of 1 over 1 plus x. I know the answer is going to be infinity, but I don't know if it's going to be positive infinity or negative infinity. If I approach it from negative 1 side, it's going to be, suppose, negative 1.9 from the left side, negative 1.91. This is going to be negative because 1 is positive. And they're approaching negative 1 from the right side. From the right side of 1 over 1 plus x is going to be positive infinity. Now I have the domain, and at the same time, I have, okay, I found the vertical asymptote. I did step 1 and 3 here. I'm going to do a step 2, which is like, that matter doesn't, the order doesn't matter. We're going to try to follow the order. Now, in step 3, find the x-intercept and the y-intercept. Okay, the y-intercept is when y-intercept, x has to be 0. And when x is 0, y equal 1, I mean, the point of y-intercept is going to be 0, 1. Now, the x-intercept is when y equals 0, and the function 1 over 1 plus x is never 0 because the denominator is a constant 1. The denominator can be 0. I mean, if it's 0, negative 1, but it's go to infinity. But if only when the denominator equal to 0 in that particular case, because this is a rational function. I mean, there's no x-intercept. Now, let's go to the next step, which is I already find the vertical and horizontal, the vertical asymptote. The horizontal asymptote, let me go to step 3 also, step 3 part B, and let's find a horizontal asymptote. Delete this. asymptote. Let's test the limit again. The limit, but the limit now is when x approaches positive infinity or negative infinity. Limit when x approaches positive infinity of 1 plus 1 plus x. Okay, the greater the x, the greater the denominator, and in positive way, positive, that means you're gonna be positive infinity here. It's gonna be 0, sorry. 1 over infinity is 0, but in the positive way, 0 above the x-axis, because the y is gonna be positive. That means it's gonna be 0. The limit of this function when x approaches positive infinity is gonna be 0, but above the x-axis. And now let's do the limit when x approaches negative infinity of 1 over 1 plus x. The denominator is getting bigger, but in negative way. That means it's gonna be 0, but it's gonna be below under the x-axis. Now we have an idea. Okay, so far we can have this. We have this. The function intercepts in the y at 0, 1. Here is 1. The function intercept, there's no x-intercept. There's a vertical asymptote at -1. I'm gonna put the vertical in yellow. Let me go back because this is now. I'll put a vertical asymptote here. -1. I know from the left side of -1, the function goes to negative infinity. And from the right side goes to positive infinity. That's the only thing I know so far. Also, I know that the x-axis is a horizontal asymptote. In infinity, it getting closer to that, but below the x-axis. And here it's getting very close to the x-axis, but from above the x-axis. Now we have so far this. Going back to the next step, which is finding the critical point. For the critical point, we're gonna find the first derivative of 1 plus x to the -1, which is the first derivative -1, 1 plus x to the -2, which it can be rewritten in -1 over 1 plus x squared. Now you see here that the first derivative is never 0, and it's always negative because the denominator is always positive because it's the second power here, and -1 is always negative, the constant. I mean, the function is decreasing all the time. That means we didn't have any zeros here. If the function is decreasing all the time, probably the function is decreasing from negative infinity. We forgot the domain here. No, the domain is already a number except -1. Okay, now the function is decreasing in all its domain. Now it's gonna be decreasing here, decreasing all the time. Now decreasing. Here we already have the graph because I know with high probability that the second derivative is gonna be concave down from negative infinity to -1, and concave up from positive infinity from -1 to positive infinity. Now let's see the steps here. There's no, okay, let's do the second derivative. We found the monotony. I mean, the function is decreasing. The function f of x equal 1 over 1 plus x is decreasing its domain. Now let's do the second derivative. The second derivative is -2 go to the front, which is times -1 gonna be +2. 1 plus x to the -3 to the -3 can be written in 2 divided 1 plus x to the third power. And here we don't have an inflection point because it's never 0. This is never 0. But then we know that this is gonna be negative from numbers less than -1 because -1 is supposed -2. 1 minus -2, -1 to the third power is negative. And then we on the left of -1, the second derivative is negative. On the right of -1, the second derivative is positive. I mean, the function is going to be concave up. From infinity to -1, the function will be concave down. Concave down. And from -1 to positive infinity, the function is going to be concave up. Now, this is the graph of the function. We don't have to do something more. This is a pretty much the graph. Now let's do another one, which is literally have some critical points. Let's do the graph of the function f of x equals, let's say 1 plus 1 over x squared plus 1. Now, this one is interesting here. We can rewrite this as x squared plus 1 to the -1. And we can find domain. And domain is all real numbers. All real numbers. Because the denominator is never 0. Because x squared is always positive. And there's no way of canceling the 1 with x squared. And the 1 is positive. All real numbers. Now, all real number is the domain. No problem in the domain. If the denominator is, if the domain is all real number, there's no vertical asymptotes. Let's find the y-intercepts. The y-intercept when x equal to 0, and when x equal to 0, y equals to 1. I mean, there's a y-intercept here at point 0, 1. There's no x-intercept, no x-intercepts. Because that function is never 0. Now, vertical asymptote, no vertical asymptote. Because the domain is all real number. And the vertical asymptote is never in the domain. Because the domain is all real numbers. Now, horizontal asymptotes, let's see here. Horizontal asymptote. Okay, before going to horizontal, there's no number A. Why say no vertical? For being a vertical asymptote, the line has to be x equal A. and there is no a when x approaches a of that function, then you're gonna get this positive or negative infinity. There's no such a number there. That's why there's no vertical asymptote. Now horizontal asymptote, let's see, when x approaches positive infinity of 1 over x squared plus 1 is going to be 0 and above the x-axis, because this is always positive. The denominator is getting bigger and bigger. 1 over infinity is 0 above x-axis, because this function is always positive. And the same thing happens when you approach this to negative infinity, because the function f of x is always positive. Now I know the function is all the time over the x-axis. There's no graph under the x-axis, and I can do something here. Okay, I'm gonna do a sketch, little sketch here. I know the function have a y-intercept at 0, 1. I know the function is getting closer to infinity, to the x-axis when x go to positive or negative infinity. But I don't know what happened in between. I know there's nothing here. I know that, because the function is always positive. But I don't know what happened in between here. For knowing what happened in between, we need to find the first derivative. The function is y equal 1 plus x squared to the negative 1. The first derivative is negative 1 plus x squared to the negative 2 times the derivative of the inside by the chain rule, 2x. We can be reading as negative 2x over 1 plus x squared to the second power. Now the first derivative you can see is equal to 0 when x equal to 0. And then we're gonna do the line test to see if that number, that point x0, comma 1, point, sorry, if the point 0, comma 1 is a maximum or a minimum. Let's see here the line test with 0 here. If we pick a negative from the first derivative, negative 1, for example, times negative 2 is positive. The bottom is always positive. I mean, the answer is gonna be positive here. And if you pick a number on the right of negative 2, you put right of 0, sorry, you pick 1, you get negative. And you have a local maximum because you change it from increasing to decreasing. And now we know that this is a local maximum. But look at this, the local maximum, the concavity is concave down, and here is concave up. That means there has to be some inflection point. By logic, we have an inflection point also. Somehow here we have inflection point. And we figure out this is 0, and we don't find the inflection point. Now the function is, we can, by the line test, we can see that the function is increasing from negative infinity to 0 and decreasing. There's a proof here. There's a proof from 0 to positive infinity. And you see the graph increasing by concavity is changing to get the maximum and decreasing on the right side of the y-axis. Now let's do the second derivative. to find concavity, the second derivative is gonna be positive 4. Now we have the I'm gonna do the second derivative using the quotient rule rather than the chain rule. I'm gonna use this. Now the bottom is gonna be powered by 2, 1 plus x squared to the bottom to the second power is gonna be to the 4th power. The derivative of the top is gonna be -2, sorry, times the bottom, which is 1 plus x squared, the bottom of the first derivative, minus the top, which is already -2x, times the derivative of the bottom, which is gonna be 2 to the front, 1 plus x squared, times the derivative of the inside is 2x. Let's see what I can do here. The second derivative here is more complicated. You have to be very careful with the algebra. Now, let's factor out from the top 2, 1, 2 here, and 1 plus x squared, one of them. And then in the first part, I get -1 plus x squared, negative times negative positive, I fact positive 2x, 1 2 is out, times another 2x. Let's see if I did it right, over the same thing, 1 plus x squared to the 4th power. Now I have the second derivative equals 2. I'm doing algebra here. And here it's gonna be in the -1 minus x squared plus 4x squared over 1 plus x to the 3rd power. Now the second derivative is gonna be 2 times, this is gonna be 4x squared minus 1 squared, gonna be 3 squared minus 1 over 1 plus x squared to the 3rd power. Now let's see when this is equal to 0. When the numerator is equal to 0, when 3x squared equal minus 1 equal to 0, when x squared equal 3 squared equal to 1, when x squared equal to 1 over 3, when x equal plus or minus a square root of 3 over 3. Now we found a square root of 3 over 3. This is the inflection point part of the x, square root of 3 over 3, and it's probably square root of 3 over 3. Those are the numbers of the second derivative positive. If is 0, sorry. Now they do the line test. I'm gonna put 0 in the middle, negative square root of 3 over 3, positive square root of 3 over 3. Let's pick 0, which is on the right part of this one, on the left side of this one. If we plug it in 0 in the second derivative, we get a negative. I mean, the function is concave down here. And we put a 1 here. The 1, we get a 1, we get a positive because 3 times 1, we get a positive. And -1 also, we get a positive because -1 squared is 1. That means concave down here, concave up here. I mean, the inflection, the function is concave up from -infinity to negative square root of 3 over 3, and concave down from the square root 3/3 positive infinity. And now we have the graph. And let's see, the function is, let's find the full inflection point. It's gonna be f of x is gonna be f of x. The function is f of x equal 1/1 plus x squared. If we evaluate, it's gonna be symmetric to the y-axis, and then it's gonna be like a, doesn't matter, plus or minus 1 of the square root of 3. Then I got 1/1 plus the square root of 3 is gonna be 1/3. We're gonna be here 1/, then gonna be 3, it's gonna be 3 plus 1, it's gonna be 3/4. This is gonna be the inflection point, is gonna be 0.1 square root 1 of the square root of 3, comma 3/4, and 0.2 negative 1 over the square root of 3, positive 3/4. And now we have the graph. The graph 3/4 is less than 1. We have absolute maximum and local maximum 1. 3/4 is less than 1, of course. Now we have 1 of the square root of 3 around here. Negative 1 over the square root of 3. Positive 1 over the square root of 3. 3/4 here. And 3/4. And 3/4 here. We have the increasing by concave up, increasing concave up, changes to concave down, but increasing. Now after 0, start decreasing by concave down. After the inflection point, start decreasing by concave up, and then getting closer to the x-axis because the horizontal asymptote. This is the graph of this function. Another way you do almost every graph. For example, the square root of x, y equal the square root of x. Very simple. Domain all x is greater than or equal to 0. Then no vertical asymptote, there's no denominator because it's the irrational function. Now, we can rewrite that x equal 1/2. The first derivative gives me 1/2 minus 1 is, and then you go down. If s greater than 0, this is always positive, then the function is always increasing. And it's easy graph because now you go increasing all the time. Let's see if it concave up, concave down, because it could be increasing like this or increasing like this. And then we'll do the second derivative, which is, let's do the first derivative was, the first one is, really I'm gonna rewrite it, 1/2 x to the negative 1/2. And the second derivative is gonna be negative 1/4 x to the negative 3/2, which is gonna be negative 1/4 over, let's do the square root of x to the third power. And now let's do the line test, because there was no critical point. The first derivative is never 0. But it's always positive. But the second derivative, because if x is greater than 0, the domain is greater than 0, this is always negative. And if always negative, the y equal square root of x is always concave down. Look, and now I have here Sorry. If I graph the function, look like this, increasing concave down all the time. Now, yeah, now we have, I gave you 3 examples. I can give you more, but if you follow those steps, you can graph any real function. Steps are, you find the domain, you find the domain and the range, you find the x and y intercepts, you find the vertical and horizontal asymptotes, you find the critical points, you find the local maximum minimum, you find the monotony, you find the inflection points, you find the concavity, and you sketch the graph. That doesn't mean you have to do all the steps, because sometimes the functions with 4 steps you can find you can sketch the function. Pretty accurate. Now, thank you for listening to the video.